Actually, there is a problem. Anyway, so is that okay now? Okay. So anyway, good morning, everyone. Actually, in this room and then who are watching online. Today, for the school, it's going to be talk or the whole day talks. We have three talks actually. The first one in the morning and another two in the afternoon. In the morning, we have here Saikat Chakraborty, right? Okay, he is a postdoctoral researcher at our institute, the IF. Okay, he's working on cosmology, actually, on this topic on that something to do with the perturbation theory on cosmology, right? And then today he's going to give like introductory something on this kind of topic, right? Okay, let's welcome the Saikat. Okay. Okay.
Okay, so thank you, Sikarin, for the kind introduction. As you can see, it's not going to be exactly like a seminar, but it's going to be more like a pedagogical lecture by which I will try to introduce you people to cosmological perturbation theory. Cosmological perturbation theory is something very important in cosmology research, and keeping in mind that maybe the students here do not have a background in GR, so I tried to introduce the various concepts of cosmological perturbation theory using some backgrounds that you are expected to have right now, like Newtonian gravity and fluid dynamics, etc. So let's get started. The various measurements show that the universe was very. Is okay? Yeah. So various measurements show that the universe was very homogeneous and isotropic at very early times. Although, of course, now we see structures in the universe, like galaxies and galaxy clusters and superclusters and everything. But still, if you average over a large distance scale, say a few megaparsecs, these inhomogeneities are still small, and these inhomogeneities actually form through something called gravitational instability. What's gravitational instability? It's like this. Suppose, so just a minute, Sikarin, I have up to 12:30, right? I have up to 12:30. I have time up to 12:30.
Yeah.
Oh, yeah. Okay. So yeah, I'll try to be more, explaining deeply. So suppose you have a homogeneous distribution, and somewhere you have a slight region of high density. And what gravitational instability says basically is matter gets more attracted to these regions of high density, which amplifies the already existing inhomogeneity. I'll show you a picture in the next slide. But the thing is, these kind of inhomogeneities, which, as I said, over a large distance scale is small, that can be the analysis of such inhomogeneities in a homogeneous background. This is called cosmological perturbation analysis. So they are like perturbations on a homogeneous background. here is a pictorial representation. So suppose matter in the universe was distributed homogeneously, and in this region there was, in this region and this region, there was, say, small high density regions, and in this region and this region there was small under density region. Okay, so what happens, because gravity is attractive, this high density region actually suck more matter out of this low density region. So effectively here we get a void, here we get a void, and in these places we get clumps. So these clumps and voids, these are the outcomes of gravitational instability. Now if you still average over a very large scale, these inhomogeneities are like small scale inhomogeneities in an otherwise homogeneous background, which is why we consider it as cosmological perturbations. Now the complete general relativistic cosmological perturbation theory is of course quite involved. So I want to, as I said, I want to give you some taste of perturbations using Newtonian gravity and using Newtonian gravity and fluid dynamics. Now strictly speaking, Newtonian gravity, the results of Newtonian perturbation theory, they are realistically applicable only when matter is non-relativistic, of course, because it's Newtonian, and on a scale which is much smaller than something called Hubble horizon. I don't know if you yet know what a Hubble horizon is, but otherwise I think it will be introduced in your cosmology course if it has not been introduced yet. Now some of the concepts that I want to introduce to you is like scalar vector perturbations and entropy perturbations, sound speed, density contrast, Jeans length, etc. Now let us okay, by the way, since it's a pedagogical lecture, you are free to raise your hand and ask questions anytime. Okay, but yeah, make sure you understand as much as you can. Firstly, so on large scale in cosmology, matter can be described by a perfect fluid. And what I mean by perfect fluid is that at any given moment of time, it can be completely characterized by these three quantities, like energy density of the matter distribution, entropy per unit mass, and the three velocity field of the fluid. Now consider an arbitrary fluid element. Okay, now since arbitrary fluid element of volume V, and since rho is the energy density, or you can say mass density, because well, energy is equivalent to mass in special relativity. Sorry. So the total mass inside this volume is just the integration over this volume of density times volume, which is infinitesimal mass. Now the rate of change of mass inside this volume, that you can take the time derivative of this thing and take the time derivative inside the integral. So you get a time derivative of energy density integrated over the volume. But then again, how can the total mass inside this volume change? It can change if mass is going out of this volume or coming inside this volume, right? So basically it's related with the flux, and the flux through this volume is the flux through the enclosing surface of this volume is given by this quantity. So rho v, v is the 3 velocity field integrated over the enclosing surface. So d sigma is the surface element and integrated over the enclosing surface. Now using Gauss's law, the very familiar Gauss's law, we can write it as divergence of rho v. By the way, this v and this v, do not confuse it. It's the velocity field, it's the volume. Divergence of rho v integrated over the volume. So this thing is equal to this thing, and you just write the equality and put everything on the same side, so you end up with this. So because it's true for any arbitrary volume, what you get is this. This is the well-known continuity equation in fluid dynamics. Next, let us consider the Newton's second law for the fluid element. So mass times acceleration over the over the volume of the fluid. So this is the mass of an infinitesimal element, and this is the acceleration, and I integrate it over the entire volume. So this is mass times acceleration. Now what are the forces acting on the fluid element? So one force is the gravitational one. So this is the phi is the gravitational potential. So minus grad phi is the force per unit mass. Multiply it with the mass element and integrate over the volume. So you get the total gravitational force on the entire volume. There is something else. There is a force due to pressure of the surrounding fluid, and that is also affecting the element's dynamics. So this, and that is force per unit area times the area times the basically it's integrated over the area. Force per unit area is pressure. So pressure integrated over the enclosing area, that is the force due to pressure of the surrounding fluid. And again, this gravitational force is the same as here, but this thing I can again write it using Gauss's law. I can write it again using okay, it's kind of skewed. I can again write it using Gauss's law, like integral over the volume, and this velocity now, sorry, this acceleration, I can decompose it like this. It's the original, it's the usual chain rule, and the right hand side I write like this, and then I just do some algebra, like this thing can be written in the vector notation like this, and yeah, okay. And if you put everything on the same side, then what you end up with is this equation. This is the Euler equation. So we had continuity equation, we had Euler equation. There are two more equations. One is the total entropy of the element that stays conserved, which gives me the entropy conservation equation. And then definitely it's because it's a gravitating system, we have the Poisson equation. Let us write list down all the equations in the next slide. So we have the continuity equation, we have the Euler equation, we have the entropy conservation equation, we have the Poisson equation. So 5 variables, rho p, capital V, the velocity field, entropy S, and phi. Till now we had 4 equations, so we need 5 equations to to close the system so that we can solve the variables independently. So we have to complement the system by giving an equation of state. An equation of state is basically a relation between pressure, energy density, and entropy. So you have to provide this by hand, and then you can solve the system totally. Now, as I said, these inhomogeneities are small on large scales, so that's why it can be treated as perturbations on a homogeneous background. And the basic concept of linear perturbation theory is that whenever we have terms like this, so this bar, whenever we have bar are like background quantities, and delta is of course perturbation quantities. So basically in linear perturbation theory, we ignore any term that is second order perturbation. So like if we have this, we ignore the delta A, delta B. So we have only linear perturbations. Okay. So this is one of the key concepts in cosmological perturbation theory. Another key concept is Fourier modes of perturbations. So this is a Fourier transformation, as we know. So suppose first any quantity A, and the perturbations are usually inhomogeneous. So it depends on time as well as space, right? And you can write this using Fourier transformations. So this delta A k are like Fourier modes. Now, what does this mean? This means that earlier you had an arbitrary perturbation quantity, and when you decompose it into Fourier, you write the Fourier integral like this. So integral is a continuous sum, right? So basically it's a sum of plane waves. So it's a weighted sum of plane waves. So any random perturbation quantity can be decomposed into a weighted sum of plane waves, and these Fourier modes, they are like the weights. And for any Fourier modes, for any plane wave mode, the wavelength is given by 2 pi divided by k, which is the k is the wave vector. So basically any arbitrary perturbation quantity is decomposed into a number of plane waves. That is what this Fourier decomposition implies here. Yes. Okay, so suppose I have two quantities A and B. Yes, A and B multiplication. Okay, and A has a background part which is A bar. So whenever we see bar, so it means background. Okay.
Yeah, I think so. Okay. Thanks.
Okay. It's okay now? There are some echoes, I guess. Okay. So this A and B, this can be any quantity. Say it can be rho or S or phi or V or P, any quantity. Okay, there's I mean, it has nothing to do with past or present. Okay, so we are considering perturbation on a background. So any physical quantity will have one background part, and on top of it one perturbation part. Okay, so for example, this energy density. At any point, energy density will have a background part, which is same in, I mean, in a homogeneous background, which is same at all points, but there is also a perturbation part, which is different at different points. Okay, and these perturbations are small. So because it's small, this is also a small quantity, this is also a small quantity, but this is a super small quantity, second order smallness. So we just ignore this thing. Okay, okay. Okay, let's go to the applications now. And any other questions from the part that I covered? Okay, if not, okay, let's first apply the concepts to just ordinary fluid dynamics. So first, let us consider static fluid. Static fluid means at the background level, the velocity field is fluid velocity is 0, and ignore gravity because well, we are applying in the ordinary fluid dynamics, we are just ignoring gravity. So ignoring gravity means this gravitational potential is constant, so no force. And also we assume that the fluid is something called barotropic fluid. What is a barotropic fluid? See, earlier I said an equation of state of the fluid can be a function, I mean, the pressure can be a function of energy density and entropy. A barotropic fluid means it's only a function of energy density. Okay, so it's a simplification. It's just meant to introduce concepts to you. Huh? No. So let us write the continuity equation first. Now, since V is 0, first let us see what kind of background solutions this situation gives rise to. So V is 0, so that means we are left with only del rho del t equals to 0. Now Euler's equation, so yeah, this equation I have written it like this, and since V is 0, this whole part is 0, so we are left with grad P equals to 0, which is basically P prime rho, and grad rho equals times grad rho equals to 0. Now unless you are considering a very special case where P prime rho becomes 0, this usually, in general, this means grad rho equals to 0. So del rho del t equals to 0, grad rho equals to 0. Time and spatial derivative both vanish, so rho must be a constant, just a constant. And since P equals to P rho, P must also be a constant. So the background solutions are like rho equals to constant, P equals to constant, V equals to 0. And when we apply small perturbations, then we just, the perturbed rho is background plus perturbation, perturbed P is background plus perturbation, perturbed V is background plus perturbation, but there is no background in static fluid, so it's just perturbations, delta V. And all these perturbation quantities are different at different points in space. Okay, because these are random perturbations, different at different points in space. Now let us write let us put these perturbed quantities in the equations. So if I put the perturbed quantities in the continuity equation, so I put rho bar plus delta rho, and in place of V bar just delta V. So what we are left with is this equation, equation 1. Similarly, let us put the perturbed quantities back in Euler equation. Yeah, you just put it there, and what utilize the information that rho bar and P bar are constants, and of course V bar is 0, so it's just delta V there, and ignore all the second order terms like delta rho delta V terms or delta V terms. All those things we just ignore. So for example, this term is like delta V. So it's already a second order in perturbation, so we just ignore that term. It's a second order smallness. So put the perturbed quantities back in the equation and just linearize. So what you are left with the linearly perturbed Euler equation. So linearly perturbed continuity equation, linearly perturbed Euler equation. Now in general, for a perfect fluid, as I said, P can be a function of both energy density and entropy. So if you write delta P has two parts. This is the chain rule. So one part, this derivative of p with respect to rho at constant s, this gives you the sound speed, because as I know, sound speed is the propagation speed of adiabatic perturbations in a fluid. And there is another part which is derivative of p with respect to entropy and at constant energy density. So we call this part sigma, just I have given a name, but this part is multiplied to entropy perturbations. So in general, for a perfect fluid, you do get both energy density perturbation and entropy perturbation, and yeah, so basically this entropy perturbation gives rise to a contribution of delta P that is called non-adiabatic pressure perturbation. Now for a barotropic fluid, P is only function of P rho. So basically there is no entropy perturbation. So you can just write sound speed as del P del rho. Okay, no at constant S is required. So C square is del P del rho. So this quantity here becomes C square, because we are considering a barotropic fluid here. In the next section, I will consider perfect fluid. And if you just combine these two equations like this, time derivative of the first minus space derivative of the second, what you end up with is this equation. This is the equation for, this is a wave equation basically, and it's a wave equation for sound waves, because there is no adiabatic no entropy perturbations. So the perturbation in the fluid is adiabatic, and it's giving rise, this thing gives you the equation for propagation of this adiabatic perturbation. So they are just like sound waves. Now it's a partial differential equation. Okay, how can I solve this? Okay, to solve this, what we utilize is the Fourier transformation that I showed you earlier, and it is a very important trick. It is a trick that you will see everywhere if you later study cosmological perturbations, which definitely you will study if you do cosmology later on. Now to solve this perturbation equation, what we do is we use this Fourier integral and put that back here in this equation. So what we get is this equation, this quantity minus this quantity equals to 0. And then firstly, we can take this space derivative inside the integral, because the integral is over the k, the wave number, and we just take the space derivative inside and utilize this result. So we end up with this equation. Okay, now as I said, this integral is basically a continuous sum, right? So this is like this whole result is like a sum over different Fourier modes, you see, different plane wave modes. Now these different plane wave modes are linearly independent, because this e to the I k dot x for different k, they gives rise to a vector space. and yeah, it's like an infinite dimensional vector space. So each coefficient is independently 0. It's like that. If you have an integral over sine mx for different m, I guess the coefficients are individually 0. So it's the same thing. So you can put the coefficients to individually 0, and this gives you the perturbation equation for each of the Fourier modes. So the Fourier modes, different plane wave modes, were only functions of time. Better to say the wave, the weight of these different Fourier modes. We call it the Fourier modes of the perturbation. So Fourier modes are only functions of time. So what we could achieve using the Fourier transformation is we transform the PDE, the partial differential equation, to the ordinary differential equation. And this thing has a problem, I guess. I mean, this does not point out properly. Anyway, so the solution of these equations is a second order equation. So second order linear differential equation. So the solution is a linear combination of these two solutions, e to the plus IKT and e to the minus IKT, and these coefficients, because I am taking the kth mode, so these coefficients also correspond to the kth mode, and this omega k is nothing but Cs times k. These are just renaming. Now suppose you want to know how the actual perturbation, so that is how the different Fourier modes behave. Now you want to know how the actual perturbation behaves. So you just put that thing back into the the Fourier integral. So I put in place of this delta rho k the solution that I got in the earlier slide, and then I get the e to the ikx inside. So I get this quantity and this quantity, and this quantity I keep as it is, but what do I do with this quantity? See, it's an integral over the infinite k space, right? So I just change the variable from k to minus k, and the integral remains the same because it's an integral over the entire k space. I guess you see this trick a lot in quantum field theory, I guess. So basically what I end up with this quantity, this whole expression, where I have used this k to minus k here. So now what I do, I put the e to the I x equals to cos x plus I sin x, that thing. So I end up with this quantity. Now I know that delta rho x, so this delta rho, it's the perturbation in the real space, right? So it has to be real. So for this has to be real, of course this imaginary term here must vanish. So this relation must be satisfied. For example, if I have this need not vanish, but what happened? This need not vanish, but this thing has to be an imaginary quantity, so that I times I becomes real. So that's why this relation has to satisfy, so that if Ck is like this, what you get is this thing. So basically, these Ck and Dk are not totally independent. They are like they must satisfy these relations, so that at the real space they are the perturbations are real. Now everything is real here. But notice something. So Fourier, what does Fourier transformations do? Fourier transformation goes from X space to K space. Okay, to convert PDE into ODE, but it does not messes up with how things evolve in time. Okay, so for example, the Fourier mode had this time dynamics, and even the delta rho in the real space, they also have the same time dynamics basically. So if you use this relation, you can also express the Fourier mode time dynamics as cos omega t and sin omega t, just like this. So Fourier transformation does not messes up with time dynamics. So usually in cosmology, when we say how does a perturbation evolves, we usually just content ourselves with understanding how perturbations evolve in Fourier space. Okay, so we just investigate the dynamics of the Fourier modes, and that's it. Okay, so up to this point, any question? Okay, if not question, then let us go to the next topic, which is in the next section. I would like to consider a static fluid, as I considered earlier, a static fluid, but self-gravitating. So this is a difference from the earlier part. So I am now not considering the gravitational potential to be a constant, but there is gravity. There is gravitational force, and I also consider the background to be homogeneous. So the fluid is homogeneously distributed over the over the entire space. And here I slightly generalize a bit. I have taken not barotropic fluid, but it can be a generic perfect fluid. So P can be a function of both rho and S. Like before, just let us find out first what kind of background solutions it gives rise to. So I put these things in the continuity equation first. Since V is 0, I have all this thing is 0. So I get del rho del t equals to 0. So again, rho equals to rho bar, which is a constant. Because I have assumed the fluid is homogeneously distributed, the background solution can already not be dependent on space, and I got del rho del t equals to 0. So it also does not depend on time. So it's rho bar, just a constant. Okay, now let us put things in Euler equation. Since V is 0, I have this whole left hand side is 0. On the right hand side, I have this quantity. Notice that now I cannot write it as before, like P prime rho grad rho, because now P is not a function of rho. But anyway, since it's a homogeneous distribution at the background level, So the spatial derivative again must vanish. So this is also vanish. What we are left with is this thing. The spatial derivative of phi, the gravitational potential, is vanishing, which gives us a problem, because now I also have the Poisson equation. If you take this another spatial derivative of this relation, you get Laplacian of phi equals to 0, not 4 pi g rho. So unless and until you have rho bar equals to 0, which is like no matter, clearly these two equations are inconsistent. So this implies the static and self-gravitating fluid, which is distributed over an infinite span of space, is just physically not possible. Okay, sorry. But so this whole case is just a simplifying assumption. I have just introduced this case as a prototype to show you how something called gene scale arises. In the next section, I will go to the realistic case. Okay, so consider this case as only a prototype. Again, I introduce small perturbations, rho equals to basically all these things, and the background velocity, background part of velocity field is again 0 because static fluid. Okay, now I write the equations again: continuity equation, Euler equation, entropy conservation, and Poisson equation, and of course rho bar and p bar equals to constant, so I did not write the equation of state, and I give linear perturbations. And now since I have taken a since I have taken a perfect fluid, not necessarily a barotropic fluid, so I will get both these contribution, like C square times delta rho and also that non-adiabatic pressure perturbation, and I put everything back into those equations and I linearize. Okay, and what I am left with is these equations, these 4 equations. So perturbed continuity, perturbed Euler, perturbed entropy conservation, perturbed Poisson equation. Now perturbed continuity, Euler and Poisson equation, they can be combined to give me this master equation on how density perturbation evolves. Okay, and see, I could, because I have considered not a barotropic fluid but a generic perfect fluid, I could not get rid of this entropy perturbation here. I just cannot. In the earlier case, I did the equation of density perturbation was totally homogeneous, a homogeneous differential equation. Here is not a homogeneous differential equation, it's a inhomogeneous differential equation because of entropy perturbation. So entropy perturbation is, when they exist, they are kind of problem. So it's again a partial differential equation, and I go to Fourier space, and what I get is this equation. Now what I do is I define something called Kj like this. So basically I take the CSS square common and then it's k square here, and I take the Cs square in the denominator of 4 pi g rho bar, and I call this quantity as kj square. So introducing kj, I can write this quantity as I can write this equation in this form. Okay. Now, when you have entropy perturbation, your differential equation is inhomogeneous. So basically, you have to go to the solution of inhomogeneous differential equation is like solution of the homogeneous differential equation plus particular solutions. It's a mathematical physics, and particular solution. Well, finding these particular solutions is kind of difficult, but you can in principle do it. But I just in the next slide, I just chose to confine myself to adiabatic perturbations, which is mostly done in cosmology. It's not the completely generic thing to do, but which is mostly done in cosmology. What I intended to show that entropy perturbation, when they exist, they act like a source term to density perturbations. Okay. It's like a it's like a source term. Okay, so this kj, which I introduced in the last slide, is called gene scale. It's precisely because I want to introduce to the gene scale, I considered this hypothetical case of static self-gravitating fluid. And corresponding to a gene scale, because this kj is like a wave number, you can define a wavelength, which is 2 pi divided by wave number, which is this quantity. This is called Jeans wavelength. Sometimes gene scale is also used interchangeably with Jeans wavelength. As I said, for simplicity, now I consider adiabatic perturbations, because otherwise I would have to find particular solutions. So when adiabatic perturbation is considered, the perturbation equation is like this. Okay. See, what's the difference with the earlier case, which is where there was no gravity? It's only this thing, kj. So because of this kj, the kj part was not there in when gravity was absent, when we did not consider gravity. So we considered gravity. The effect of gravity is to introduce a scale. This is an important thing. The effect of gravity is to introduce a separate scale here, and the qualitative behavior of perturbations of plane wave modes of perturbations. So basically this rho k for wavelengths higher and lower than the Jeans wavelengths are different. So this is like a cutoff scale which differentiates two separate behaviors. So we did not have this thing when gravity was not considered. So the contribution of gravity is to introduce this cutoff scale. So when we have so for those plane wave modes whose wavelength is more than the Jeans wavelength, how do they behave? So for them k is less than kj. So you can just solve it, because k and kj are constant, and you get this exponential plus minus solutions. So two linearly independent solutions. The general solution is a linear combination of these two solutions. One solution is exponentially growing mode, the plus e to the plus thing, and another solution is exponentially decaying mode, e to the minus thing. So this is how higher wavelength modes behave. How does plane wave modes whose wavelength is lower than the Jeans wavelength, they behave? In that case, this thing is positive because lambda is less than lambda j, k is greater than kj. So I still get exponential, but plus minus I appears here. So this is like oscillatory solutions. So the complete solution is a linear combination between two oscillating modes. You see, we got only oscillating modes in the earlier case because there was no gravity, there was no cutoff scale. So only one kind of behavior, but here I have a cutoff scale and I have different behaviors below the cutoff scale, above the cutoff scale. So as I said, Jeans scale is a cutoff scale separating these two behaviors. Now, if we want to consider the behavior of perturbations in a scale which is much lower than Jeans wavelength, so suppose we want to, the Jeans wavelength is, because Jeans wavelength is constant, right? So suppose Jeans wavelength is like this, and we confine our attention to a size scale like this. Okay, so in this case, we have to take into account only those plane wave modes whose wavelength is up to this. So they are like, only those plane wave modes are important whose wavelength is much smaller than the Jeans scale. So if we consider the behavior of, if we are interested in this scale and we have to consider behavior of perturbation mode whose behavior of perturbation modes whose wavelength is much smaller than the Jeans wavelength, then we can just approximate this equation like this, and this is the same equation we obtained earlier, and the equations are, and the this is the plane wave equation that we obtained earlier, and the solutions are sound waves, exactly the same what we obtained earlier. Okay, so at a small scale, it's as if the effect of gravity is very subdominant. So we get the same kind of solution. But now, if you want to consider the behavior of perturbation in a scale which is much higher than the Jeans wavelength. Okay, so suppose Jeans wavelength is this. I want to consider, a length scale. So in cosmology, you always work in a length scale. So I want to consider this length scale, and so of course those perturbation plane wave modes will be important for me, which has wavelengths much higher than Jeans wavelength. So for those kind of modes, this equation can be approximated like this, because k is much less than kj, and then the solutions are e to the plus minus, basically exponential solutions, not oscillating solutions. And I have just introduced quantity tau to show that to write it in a different way. And if you can as well as before, you can also find the behavior of perturbations in real space So you just put this solution over inside, and what you get is this. So as time goes on, this mode is decaying. So this mode decays fast, but this mode grows. Okay, so one part of the perturbation, they just grows exponentially, and this exponential growth of perturbations, which tries to drive the universe exponentially out of homogeneity, this is called Jeans instability. Okay. So this Jeans wavelength, which can be written as 2 pi Cs times tau in terms of this tau. This is called sound communication scale. So above this scale, gravitational instability is dominant. Okay, so the universe, the perturbation is exponentially growing, and when perturbation in a gravitational gravitating system is growing, it means that the system wants to clump. Okay, the system wants to clump. And below this scale, the pressure is actually balancing, the pressure is dominant, so it actually balances the gravitational clumping. So when it balances the gravitational clumping and the pressure is tries to push out, so what you get is a balance and basically a plane waves like sound waves. So below this scale, you get the ordinary sound waves as if gravity is absent, and above this scale, you cannot just ignore gravity. The gravity is dominant. Any question up to this part? Okay, then let me just introduce vector perturbations. So if I now make all the scalar perturbation quantities vanish from all the equations, what are the scalar perturbation quantity? Delta rho, delta s, delta phi. I make everything vanish. What we are left with? We are left with a perturbed continuity equation where I have made delta rho vanish. So I have this quantity, I have this expression, and I also have perturbed Euler equation where I made delta rho, delta s, delta phi vanish. I have this equation. So basically, spatial derivative and temporal derivative of this fluid velocity, which is the only vector quantity here. Fluid velocity perturbation, sorry. So I have made, both of them vanish. And this fluid velocity is perturbation is also a perturbation quantity. So again, like any perturbation quantity, it can also be decomposed by the Fourier transformation into plane wave modes, and so which is exactly what I did here. Okay, first of all, this thing that the temporal derivative vanish, it means that this thing is constant in time. So delta v is just constant if it's it does not evolve with time. So if initially it was 0, it stays 0. If initially there was some fluid velocity perturbation, it stays the same. And if I use the Fourier transformation now, this delta Vk will just be constants, because earlier, say for delta rho k, these was functions of time, but now it cannot be functions of time. There is, because the Fourier because the actual perturbation is constant, Fourier mode is also constant. with constant delta Vk. And now if I use this also here in this equation, what I get is, after I do it, I get this thing. So it's like this. For all the plane wave modes, each of these plane wave modes has a, because it's a plane wave, it has a wave vector, right? Wave vector is k. And the velocity, the small velocity, perturbative velocity of each of these plane wave is actually perpendicular to it, perpendicular to the wave vector. So if I have this Cartesian space, and I have a plane wave plane wave perturbation whose wave vector is this way, so my fluid velocity perturbation corresponding to this plane wave mode is confined to in this perpendicular surface, the plane surface perpendicular to the wave vector. So it's like even though delta V is a vector quantity which may have 3 components, okay, but because there is this constraint, so there is actually 2 independent modes of perturbation. So 3 components, 1 constraint, so just 2 independent modes of fluid velocity perturbation. So there is 2 independent vector perturbation modes. Also, these vector perturbations exists and evolves. In this case, they do not evolve, so they just exist independently of scalar perturbations, because see, in the scalar perturbation equation, like for example this one or this one, there was no fluid velocity perturbation. And also, even if I considered zero scalar perturbation, I could still get vector perturbations. So these vector perturbations exist independently of scalar perturbations at the linear level. Okay, we are considering linear perturbations. So if you study the actual cosmological perturbation theory later on, you will see that at the linear level, scalar, vector and tensor perturbations. So in relativistic perturbation theory, you also have tensor perturbations because everything is tensor there, right? So all of them evolve independently, okay, at the linear perturbation level. So you are getting the same kind of concept here also. And of course, they don't evolve for a static fluid, as I said. Is okay everything, or any question? Okay. Okay, let us go to now the last section, which is the most realistic case. Okay, so which is like a self-gravitating fluid. So of course, gravitational potential is not constant, and there is a non-zero gravitational force, and the fluid is expanding according to Hubble's law. So I guess you have already been introduced to Hubble's law, because I can see here. Yeah, Hubble's law, all of you know. So like if you are here, you have the fluids around you, all the fluid particles are moving away from you according to the Hubble's law. So the fluid velocity is Hubble factor times the physical coordinate. So this is the Newtonian description of a realistic scenario of self-gravitating fluid in an expanding universe. Because I am in a Newtonian picture now, I cannot talk about expanding universe, so I talked about expanding fluid. But basically, if you are in an expanding universe and the fluid particles are just, at their respective co-moving coordinates, so it's like fluids in an expanding universe. And of course, because the background is homogeneous, I am considering the fluid distribution is also homogeneous at the background level. Again, let me see what kind of background solutions it gives rise to. I guess you will be familiar with it now, because this is the continuity equation, and since rho at the background level is homogeneous, I can get the rho out of the spatial derivative, and when you have this thing, then H is also homogeneous, so you will have only divergence of x, which is like 3. So you will get rho dot plus 3H rho equals to 0. You know this equation, I guess, already. And because you are already familiar with what is a scale factor, I can see there. Yeah, it's basically evolves like this. So see, this one, for example, was your generic equation, right? And the equation we got here is as if p equals to 0. And what does p equals to 0 means? The dust fluid, right? Dust fluid, non-relativistic fluid. Dust is non-relativistic. Okay, so that's why I said at the very beginning. So the results here actually correspond to actually applies to non-relativistic fluids. So now we have the Poisson equation, which is this. Now we have the Euler equation, and basically I take the divergence of this Euler equation. So it's divergence of V here, and divergence of V will give me 3H, derivative of it is 3H dot. And here I get, when I take the divergence, is this thing. You have to do a bit of vector calculus. You will need to use some identities, and then this Hubble's law you put in place of V, and what will end up with this equation. And for grad rho terms, when you take divergence and then use the Poisson equation, you get this thing. So basically you get back this equation. I think this equation is also there somewhere. Yeah, this equation, I guess. Yeah, H dot plus H square equals to minus 4 pi G times rho. P is 0, non-relativistic fluid, P is 0. Now let us use the perturbations. Let us apply perturbations. So background quantities, which is homogeneous, background matter distribution is homogeneous, and I apply perturbations. Notice that here the background velocity is not 0, it's actually Hubble's law. Okay, because the fluid is, I have already considered an expanding fluid, so the background velocity field is this, and I also have the perturbations. The perturbations are different at different points in space. As you know, it's because it's the Newtonian analog of fluids in an expanding universe, and you have already been introduced to co-moving coordinates, I guess. Yeah, so it's better to go to co-moving coordinates. So co-moving coordinates are what? Like Q, and which is related to the spatial coordinates like this. So, sorry, physical coordinates like this. The physical distance is scale factor times the moving distance. And if you introduce moving coordinates, you can relate the spatial derivative and the temporal derivative in physical and co-moving coordinates like this. So this thing is quite straightforward. From here to get to this thing, you need some, basically some algebra. But yeah, you can find this relation in cosmology books, I guess. Now, because we will entirely use the moving coordinates now on, so I will just drop the subscript q. I will just use the divergence as like this. I'll just drop the subscript q, and I will also use in this case a quantity which is delta rho by rho. This is called the density contrast. This is a very important perturbation quantity that people work with when they consider late time cosmology. And in terms of this density contrast, you can write the perturbed continuity, Euler and Poisson equation as this. Okay, for simplicity, I have gone, I am considering only adiabatic perturbations. Okay, so entropy perturbations will give to inhomogeneous differential equations. So there is no entropy conservation equations, only these three equations. So these three equations are like this. So again, all these barred quantities are like correspond to background. Okay, now just like before, I can combine the three equations like this, and because no entropy perturbation, I get a nice homogeneous differential equation. Now I have to use the Fourier transformation, but now with respect to the co-moving coordinate q, not the physical coordinate. And when I do this, I get this perturbation equation for different Fourier modes. And again, I can define this entire quantity. CS square by S square I can take outside, and whatever is there I can define it as kj square, which is my new Jeans length in this case. Okay, so like Jeans scale is this. What's the difference between from the earlier case? The only difference is this quantity here, A, because A is what? The scale factor that characterizes the evolution of the universe. Earlier I considered gravity. So Jeans scale was introduced, but there was no expansion of the universe, say, no evolution. So at the background level, there was no evolution. So the Jeans scale was constant, like 4 pi g rho bar divided by Cs. And in the earlier case, if you remember, rho bar was constant. So the Jeans scale was constant. Now, neither rho bar is constant and there is an explicit A. So Jeans scale is not constant. So the effect of expansion of the universe is to make the Jeans scale go from constant to time dependent. That's the sole effect. Now, corresponding to this Jeans scale, you can define the so-called co-moving Jeans wavelength, which is 2 pi divided by kj. Okay, just like the same way. And as like in an expanding universe, as like for any length scale, you have a co-moving scale and a physical scale, right? And the physical scale is just scale factor times the co-moving scale for any length scale. So you can correspondingly define the physical Jeans wavelength. Like A, the scale factor times the co-moving Jeans wavelength. And yeah, so it's basically this. And for example, as I showed, rho bar is 1 over a cube for non-relativistic matter, dust. So lambda j physical Jeans wavelength that evolves with time like this. This is how it depends on the scale factor. Some people also define a Jeans mass, which is like the total mass within the Jeans volume. So this is just the definition, lambda physical cube and multiplied by energy density. So the total mass within the Jeans volume. Now, what does it changes into the solutions of the perturbation equations? When I consider a length scale which is much lower than the Jeans wavelength at any particular time, because now the Jeans wavelength is a function of time, at any particular time, if I consider those modes whose wavelength is much smaller than Jeans wavelength, assuming that Cs, the sound speed, varies very slowly, like either it is constant or even if it is not exactly constant, its time evolution can be neglected with respect to the expansion of the universe. So this is whenever you see some slowly varying thing in cosmology, what we mean is that quantity can vary, but its rate of variation is very slow compared to the expansion of the universe. Expansion of the universe is in the rate a dot by a, which is like h. So Cs dot by Cs, fractional rate of change of Cs is much less than fractional rate of expansion of the universe. That's how you get Cs dot much less than HCS. Now, using this approximation, the solution of the perturbation equation, like this equation, is when you also put k much greater than kj, okay, you get these things. See, is e to the plus minus I something. So they are still sound waves in some way because it's oscillating perturbations in density distribution. So they are still sound waves, but now the amplitude of the oscillation perturbation decays because there is an A downstairs at the denominator. So as the universe expands, the scale factor grows. The oscillation is there, but its amplitude is decaying. And you can physically interpret it as follows. So this is the perturbation equation, right? See, this term is like a friction term. So if you remember the equation of motion of any system that has friction, there is a friction. For example, a mass falling down the Earth's atmosphere, and while you consider the drag due to the atmosphere. So this friction term is something that is proportional to the velocity. So you have something times x dot term. It is the same here. So delta k is like like the x. So you have some term proportional to the velocity. So it's like a drag. So basically, the expansion of the universe is like a is acting like a friction. Okay. Now, if you have something oscillating and you have a friction, so what will happen? The oscillation will decrease. So it's like, so it's the same here. Okay. the amplitude of oscillation just decays because there is this damping or friction term here in the perturbation evolution equation. So this is the only difference that the expansion of the universe creates. Earlier, when expansion of the universe was not there, this term and this term was still there, but this term was not there. The expansion of the universe introduced this term, this friction term. Now, what about the other limit when we consider the scale much greater than Jeans wavelength? So, in this scale, lambda is much greater than lambda j and k is much less than kj. You can show that a generic solution to this equation at the limit when k is much less than kj is this thing. You can basically show it. I will tell the references later on. Yeah, you can find these in these references. Now, for example, for a matter dominated universe or a dust dominated universe and spatially flat universe, I am going a little to relativistic cosmology, just a little, but I guess from whatever is covered here, you can get it, just to show you the effect of the expansion of the universe. So, for a spatially flat dust dominated universe is scale factor behaves like t to the 2/3 and h behaves like 1/t. You know it, it has been covered already. And so, if you explicitly calculate how this perturbation mode evolves, you get this. So, one part of the solution is a growing mode and another part is a decaying mode, and the total solution is a linear combination of this solution. So, as time goes on, this growing mode of course dominates, okay, because this mode is going down. So, what's the difference from the static case? In the static case, in this limit, I had a Jeans instability. So, perturbations were growing exponentially. Perturbation still grows here, okay, but in a much weaker manner. Earlier, it was growing exponentially when there was no expansion, but now it's growing only t to the 2/3, like this. Earlier, it was like. So, you can think it like this, because there was no expansion earlier, perturbations was, I mean, there was nothing to check the, the growth of perturbations. And as I said, in a gravitating system, the growth of perturbation is like gravitational clumping, right? And here you have an expansion of the universe. So, gravity is trying to clump things in, while the expansion of the universe is trying to push things out. So, there is a fight between the two. So, in this scale, gravity is still dominant because the perturbation is still growing, but of course, it has been made much weaker due to the expansion of the universe. So, this is the effect of the expansion of the universe. Now, for a barotropic fluid, just to show you, for a barotropic fluid with constant equation of state, P equals to omega rho, where this omega is a constant. So, sound speed is just equal to the equation of state, and if sound speed is equal to the equation of state, for dust fluid, equation of state parameter is 0, right? For dust, equation of state parameter is 0, so sound speed is also 0. and when sound speed is 0, the physical Jeans wavelength is also 0. So basically, if you consider a non-relativistic case, truly speaking, this limit does not matter because CS is 0. So, sorry, lambda j is 0. Lambda j is very small. So, this limit does not matter that much, truly speaking. So, these are like, the problems you get into if you want to teach cosmological perturbations using Newtonian gravity totally, but at least some of the concepts that you can introduce in Newtonian perturbation theory still goes on to actual relativistic cosmological perturbation. And also for vector perturbations, again you make all the scalar perturbations vanish. So, you are left with this equation, which again means that the small velocity perturbation of these plane waves modes are proportional to, are perpendicular to their wave vector. So, again just like as before, there are two vector perturbation modes, nothing changes here, something changes here. So, earlier this H was not there, so vector perturbation was constant in time, they did not evolve, but now they do evolve. I am sorry, there should be only one dot here, there is a typo. So, now they do evolve because they do have a equation of motion, and if you solve this equation of motion, so these vector perturbations, which are perturbation in fluid velocity, that goes down as 1 over the scale factor. So, at the linear level, vector perturbations decay in an expanding universe. So, when you will actually do relativistic cosmological perturbations later on, if you do it, you will see people do not really care about vector perturbations. So, they just introduce vector perturbations and then they say, okay, we will not consider vector perturbations. There are two reasons for it. One, the vector perturbation at the linear level, the vector perturbations exist and evolve independently of the scalar perturbations. So, nothing else can source vector perturbation. Okay. So, there is no problem if you do not consider vector perturbation, nothing else, it will not be sourced from something else. Secondly, we mostly consider expanding universe, our universe is expanding, and in an expanding universe the vector perturbation just dies away, and usually we assume there in the most dominant paradigm, we assume an inflationary phase in the very early universe where universe expanded very fast, so vector perturbations died out very fast. So, there is no vector perturbation now. Okay, so just summarizing, we considered three cases. First, without gravity and universe expansion. Without gravity and universe expansion, so we considered non-gravitating fluid and non-expanding fluid. The solutions of the perturbation equations are the usual sound waves, as we know, it's of fluid dynamics. When we consider gravity, but still a static fluid, no universe expansion, this case is of course hypothetical, as I told you, but still it serves to show that there exists a cutoff scale. So, gravity, effect of gravity is to introduce a cutoff scale, which is called Jeans scale, and when we consider no expansion of the universe,
ส
this Jeans scale is constant. Below Jeans scale, 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale factor, 1 over the scale factor is 1 over the scale the gravity is subdominant. So we still get sound waves, just like in this case when we did not consider gravity. So below gene scale, we get sound waves just like here. But above gene scale, gravity is dominant, and there is an exponential growth of perturbation which tries to clump matter together. This is called Jeans instability. Now, in the most realistic case possible with Newtonian perturbation theory, where we consider both gravity and an expansion of the universe, or in other way, in Newtonian picture, an expanding fluid, then Jeans scale is still there, this cutoff scale is still there, but it becomes time dependent. So this is what the expansion of the universe gives rise to. And below this Jeans wavelength, the solutions are still sound waves, but with decaying amplitude, and that is because the universe expansion gives you a friction term. So oscillations are decaying in amplitude. And above Jeans scale, there is still a Jeans instability, there is still growth of perturbations, but it's much weaker. Okay, just T to the 2/3 for a specially flat matter dominated case. So yeah, and that is again due to universe expansion. So while gravity is trying to clump, the universe is expanding. And I don't know if you have been introduced with Hubble horizon yet, but in relativistic perturbation theory, there is actually a scale which is called Hubble scale, and Hubble scale is a cutoff scale there in relativistic cosmological perturbation theory. So you have different behaviors above the Hubble scale, you have different behaviors below the Hubble scale. And as I told you in the very first slide, that these results of Newtonian perturbation theory, they actually they are actually valid in scales which is much smaller than the Hubble scale. So if you okay, and then also they are valid mostly for non-relativistic fluid and dust fluid, and for dust fluid, Jeans wavelength is 0. So basically you do not have this limit, so you have only this limit, and for example in this limit for specially flat dust dominated universe you get this kind of solution. And now whenever you will study actual relativistic perturbation theory, if you see how the relativistic perturbations behave in sub-Hubble scale for spatially flat matter dominated universe like this, it will be exactly this, like exactly the same. So which is why I said in the very first slide that this analysis of Newtonian perturbations can be these results can be used for non-relativistic fluid inside the Hubble scale. So they are actually consistent with the relativistic results. Okay, that's it. I hope I could introduce some of the concepts that you may need if you study cosmological perturbations, which I hope you will study later on. Okay, thank you. So,
Well, any questions you'd like to ask? มีคำถามครับ
Maybe I would like to ask what happened in the scenario if we consider in the case of the negative cosmological constant. So you said that in the actual expanding universe, the solution would be the damping oscillation. But what would be the case of negative cosmological constant? Do you have any comment?
Well, firstly, that I think cannot be considered in Newtonian theory. And but if you go to relativistic perturbation theory, we assume usually the cosmological constant to be positive, and for positive cosmological constant, because it's just a constant, there is no perturbation. So it's not like you have something something homogeneously distributed and you have perturbation on it. So it's not like that. On cosmological constant, we usually do not consider any perturbation, because we assume cosmological constant is a fundamental constant. There is a fundamental constant from the theory. So there will still be perturbations in the matter density and other things that arises in relativistic perturbations. Only these perturbations will be there, but they will evolve in an accelerating universe, and mostly they will decay. When the cosmological constant dominated phase comes into picture, they will just decay. They will not be able to clump and form structures. So for example, in cosmology, all the structures we show now, that actually formed in an epoch where cosmological constant was not that dominant. Okay, so there was a matter dominated epoch when cosmological constant was not that dominant. That's when all the structures formed. Now we are in an epoch where cosmological constant is dominant, and there is no new large scale structure forming right now. Of course, there is small scale things like supernova explosion and all these things, but no new large scale structure formation in the cosmological constant phase. But and regarding a negative cosmological constant, well, I don't know. I don't know how the background will evolve first, whether it's at all consistent with the background Einstein equation with ordinary matter. I don't know. Okay.
Okay. Well, I think you have more questions. You can discuss with Saikat during the lunch.
Yes, sure. And in case you need references, I can suggest 2 books, and both these books, in my opinion, are very good references for learning cosmology as well. And one book is called Physical Foundations of Cosmology. It's by Mukhanov. Okay, Mukhanov is a legend in cosmology. So Physical Foundations of Cosmology is the name of the book. It's written by V. Mukhanov. And another book is called just Cosmology. It's by Daniel Baumann. And it's also a very new book. And I mostly considered these 2 books to build up my material here. Both these books has a dedicated chapter on Newtonian perturbations. So most of the things that I have written in my slides. You can find in those two books. And yeah, that's it.
Okay, then let's thank Saikat again. Right, okay, I think we have lunch outside already, then please have lunch, and then the first talk in the afternoon will start at 1:30 sharply. The talk in the afternoon will be in Thai. Okay, that's it. Okay, เจอกันตอนบ่ายครึ่งครับห้องนี้นะครับควรมาให้ตรงเวลาเนาะเพราะว่าเป็นแขกข้างนอกนะครับโอเคครับ Thank you very much.
Thank you. Lunch is